2, 1. Hello everyone, and welcome to today's webinar on open and closed systems net positive suction head. So why we think this subject is important? Well, we hope that by covering this details today, it'll help you make faster and better technical decisions in the job that you do, and hopefully add something to your tool belt. So to add a little bit to your skill set and add some value to what you do. So a couple of quick notes about our viewer panel. So how to use the functions for the viewer panel during the webinar, and some technical hints. So if you have any technical problems with the webinar not functioning, just put a question in the ask a question box and someone will get back to you as quickly as possible. If you'd like to expand the view to see it full screen, just click on the double arrows there and they'll expand it to a full screen view. And we'll have an archived version of this webinar. It'll be on our the Grundfos Technical Institute website, along with any Q&A from the webinar that we don't get to in this webinar. And if you are not hearing the volume correctly, or if the slides don't seem like they're advancing properly, just click on the refresh media button or refresh your browser. There's a refresh media button that's just under the presenter's picture. And then you can control the volumes of the webcast by adjusting the volume up on your computer or down on your computer. And then a little bit about Grundfos. Grundfos is currently the world's largest pump company by volume in dollars. Over 17 million pumps produced annually. And one of the major concerns and functions for Grundfos is really focused on the world's water and climate challenges today. A little bit more about the Grundfos Technical Institute. So obviously you're using that platform for this webinar today. But some of the other items that we have on there as well are our virtual classrooms, where we have self-paced courses where you can actually, once you set up your profile, you can take the courses and it will actually track your progress through the course, as well as have some little quizzes and tests in those as well to just test your knowledge. One of the nice advantages of those is if for any reason you can't finish the whole course, if you leave and come back, it will bring you back right where you ended the last time. So you'll get the option of starting back where you left off at, or you could begin the whole course over again. So also on there are our webinars, so both our live webinars as well as our recorded webinars, so you can get to all of those. We also have our calendar, which will list all the events coming up on there as well as our face-to-face courses, which we hope to get back to here soon. We also have a link to our YouTube channel, and on the YouTube channel we'll have how-to videos, so how to do technical functions as well as how to use some of the various Grundfos products on there as well. And we also have our white papers and some of our other technical training knowledge out there also. So for our presenters today, so our main presenter for today's webinar is Jim Sweeteye. He's the Senior Technical Training Manager for the Grundfos Technical Institute. He's got an education in Bachelor of Arts from Hiram College out of Ohio, and he also has a Master of Science in Education and Curriculum Leadership out of Emporia State in Kansas. He's been in the industry for over 40 years, and he's served, done a number of different roles, everything from pumping systems for commercial HVAC. His specialties also include hydronics, industrial, and municipal application. And he's also currently a part of the Hydraulic Institute, and he's a certified trainer for a Hydraulic Institute as well. So with that, I'm going to pass the webinar over to Jim. And Jim, it's all yours.
Thank you very kindly, Kevin. This is one of my favorite photos. That's pretty ugly, isn't it? That's an impeller that's been subjected to some pretty extreme cavitation. That is not the effect of corrosion or abrasion that you're looking at. That's cavitation that did it. And we'll be taking a close look at that phenomenon and give you the ideas on how you can prevent that from happening to your centrifugal pump. So here's our objectives for today. I'll let you have a minute to read down through them. And I will point out, it's a my experience has taught me that it's a lot better off if you discover the problem before all this equipment gets bought and installed. You get it installed, then you find out you have a problem on your hands. And there's some horrible stories I could tell you, because sometimes they can be difficult or darn near impossible to fix. This webinar is not going to make you an expert on all NPSH matters, but it's going to give you the main concepts, and hopefully to encourage you to continue to study the subject. It's a pretty fascinating one. So first, we need to define a few terms. NPSH is net positive suction head, and I'm going to just pause here for a minute. That's an indication of the force that pushes liquid into the impeller of a centrifugal pump. So what this course is really about, when the impeller spins and pushes water out, it needs some force to push water into the impeller. Otherwise, you'd have a vacuum there, and that vacuum would create all kinds of problems. So this definition right here is really important. What is that force pushing liquid in? Well, there's a few others. Net positive suction head required is how much of that force is necessary for a given pump. The net positive suction head available tells us something, not that tells us everything, about what nature is providing in terms of that force to push the liquid into the eye of the impeller. There's also a new term that's being used in the industry called net positive suction head 3%, or NPSH3. And that's a Hydraulic Institute definition. And you can read that, and you want to study up on that. NPSH3 and NPSH are virtually the same thing. The NPSH3 is just a little more technical, and in that regard, you can argue it's a better definition. The world is still used to mostly using the NPSHR nomenclature, however. As I mentioned, under the wrong conditions, you get this vapor that forms in the impeller, and those bubbles collapse violently. All right, and the result is this damage that you see here. Cavitation is not the implosion of the vapor bubbles themselves. All right, cavitation is the creation of those pockmarks or cavities that you see. Cavities, that's where we get the word cavitation. The implosion of those vapor bubbles is what causes the phenomenon, but not the phenomenon itself. That's kind of a technical thing, but maybe it's an important distinction. At least it's interesting background. Consequences: cavitation. If you don't have enough force pushing in, if you don't have enough NPSHA, you're going to get this cavitation, erratic flow, vibration, noise, damage, and not just damage to the pump, but it can damage the system components as well. We're going to be looking at both open loop and closed loop piping systems today, because the cavitation, you deal with it a little bit differently as a practical matter. Here's an open loop system, and that's a system in which the pumped liquid is open to the atmosphere. Normally on the suction side. There's other circumstances under which you could have an open system. If you're pumping from a lake or a river, or a lot of other cases where open systems are found. In fact, most pumping systems on this earth are probably open. Closed loop piping systems are different. They're very common in residential hydronic applications, and then in commercial buildings and heating and cooling applications, and industrial cooling applications in particular, along with some heating applications. There's a difference with the closed loop piping system. You're using the same water, and today we're going to talk in terms of water. Bear in mind this conversation is equally important if you're not pumping water with other fluids. It can be even more critical when you've got highly volatile fluids, but we're going to talk in terms of water only today so we can understand the basic principles. With an open loop system, in effect, you're using up that water. you're pumping it off someplace and using it. With a closed loop system, you're just pushing water around that loop, and you might do that for years. My hydronic heating system in my basement essentially has the same water in it that it's had for, theoretically decades. So, again, what's this about? I mentioned that it's about the eye of the impeller. And you can see the direction of flow into our piping here. You can see where the suction piping is and where the impeller eye is. When the impeller spins, those vanes push the water outward, as you can see in that picture on the lower right. Well, and the water goes out to top discharge on this pump. In effect, though, at the center of that, since those vanes are pushing the water out and then up, in effect, you're trying to create a vacuum at the eye of the impeller. And you might remember from science class in high school, the old phrase, nature abhors a vacuum. It tries to fill that vacuum. Well, the only place the liquid can come from to fill the vacuum at the eye of the impeller is through the suction inlet of the pump and all that upstream piping. We have to get the water to the eye of the impeller to prevent a vacuum. Well, it poses the question, how strong is the force of that vacuum at the eye of the impeller that it's trying to create? How strong is that force? That's what the NPSH-R is all about, and we're going to show you how to determine that. A couple basic principles. Flow out of the pump has to equal the flow in. If we try to pump, well, we can't pump more out than we can move into it. It has to be equal. When the pump is trying to pump more out than nature is trying to push into it, that's when we run into problems. So that begs the question, well, where does that pushing in force come from? That's the strength of that force is what we call NPSH available, NPSHA. So where does it come from? We're going to answer that question for you. All right, so how is net positive suction head required determined? And we need to go to the pump curve. In almost all cases, we go to the pump curve. There's a few cases where you use a chart instead of a pump curve, but we'll get to that later. So you need to go, let's just say for now, for net positive suction head required, you can only get that from the curve. It's a characteristic of the pump when the design engineer created the pump way back when. And you, as a user or a specifying engineer, you can't do anything about it. It is what it is, and it is what the curve said, period. It's an immutable law of nature at this point. Now, there are some manufacturers that do make special low NPSH-R design pumps, but there's curves for those as well. So once again, what you see is what you get. A little bit more on NPSH-R. It's based on the flow rate. So you can see down there at the bottom of the curve, flow rates at the bottom. The NPSH you read over there on the left. So if we have a 1,000 gallon minute flow rate, as you see here, we read up to the intersection with the NPSH-R curve, and then we read off to the left. And in this case, the NPSH-R is probably about 20 feet. Okay, so that's at 1,000 gallons a minute. Now what happens at a different flow rate, at 1,500 U.S. gallons per minute? Now what is our flow rate? Or what is our NPSH required? And we read up to the intersection with the line. It occurs here. And then we read to the left. And you can see that now we have about 45 feet of NPSH-R required. That's significantly higher than that when we were at 1,000, which was only about 20 feet of head. So you can see, as a rule, the further right on the curve you get, the higher the requirement is. That's how we determine what the NPSH are. And here's a little note. As a safety factor, and this is really important to keep yourself out of trouble, you want to always add 2 to 4 feet to what's displayed on the curve as a safety factor. It will save you so much grief if you do. And if you ever have a problem with a net positive suction head issue, you'll wish you'd added some safety factor in there. So be prudent. All righty. Now, how do we calculate the net positive, or how do we determine the NPSH-A available? And we're going to deal with an open loop system first, then we'll go and look at a closed loop system. But notice the top line here, NPSH-A must be calculated. You have to calculate it. Somebody has to calculate it. Make sure it's calculated. By the way, make sure you convert all the values to feet ahead, because some of these values in the charts will be stated in pressure, in PSI. Here in our U.S. customer units, we're going to be dealing with U.S. gallons, and we're going to be dealing with feet of head and pounds of pressure. If you've probably read some long treatises on the topic of NPSH, and a lot of them make it look like some sort of really mysterious topic. Unless you've been initiated, you can't understand it. Well, the fact is, there's only 5 factors that you have to consider when you're calculating NPSH-A. And by the way, this is true for open and closed systems both. There's only 5 values. If you can come to grips with those 5 values and properly make the calculations, you're just about home free. And we're going to try to take the mystery out of those 5. So there's the formula that we're going to be using, the component parts of the formula. We have the elevation that's either above or below the pump impeller. It's generally expressed as the center line of the eye of the impeller. We have to add to that atmospheric pressure. Let me do it this way. There's our formula. And again, they'll be expressed in feet. And there's atmospheric pressure that we have to determine. There's some gauge pressure we have to look at. There's something called vapor pressure of the liquid itself. There's charts for that. And then we have to determine our suction line friction loss. So that's it. Once we learn these 5, we're in good shape. So, on this issue of elevation, that's our first step. There's the equation at the top of the screen, and elevation is the first component of these 5. And this is really important. That elevation can either be a positive or a negative value, depending on the level of the liquid above or below the eye of the impeller. Over on the left, you see scenario A. The elevation, it's a positive value because the liquid level is above the pump. And what that does, it gives us the advantage of the weight of the liquid pushing into the eye of the impeller. So we've got all that good weight working in our favor. In this scenario, you can see the liquid level is 8 feet above the center line of the impeller of the pump. So we would have 8 feet of positive value. On the negative side, we had some suction lift. You can see we're 8 feet below the pump. So that would be a negative value. So that's all there is to dealing with elevation. It's pretty straightforward. As a practical matter in the field, it might be a little more challenging, but it's still just a question of elevation differences at the end of the day. Next, we have to deal with atmospheric pressure. You can see there at the top where the bold is. That's the second factor in our equation. Now, atmospheric pressure is dependent on altitude, whether, the elevation. If you're up in the mountains, you've got less. This is a typical chart that we use to determine atmospheric pressure. At sea level, or 0 feet of altitude, that's where the red arrow is, the atmospheric pressure is 14.7 psi. And from Pump Basics, you might remember that you take psi times 2.31 to arrive at feet. And 14.7 times 2.31 is equal to 33.9 feet of head. So that's one example. Let's now take a 3,000 foot example. So, maybe we're in the upper part of the Appalachians here in the U.S., around 3,000 feet. The atmospheric pressure there is only 13.2 psi. So there's less oxygen and nitrogen and trace gases in the atmosphere, so less force pushing down. We've only got 13.2 psi helping us out. This is one of the forces that's pushing that water into the eye of the impeller, because it's pushing on the lake or the tank or whatever we're pulling out of. We take our 13.2 times the 2.31 conversion factor, and that gives us 30.4 feet of head. So that's in our favor. So in an open loop system, atmospheric pressure is always our friend in an open system. It will always be a positive value in the equation when you're pumping in any open loop system that's open or vented to atmosphere. Okay. One second while I get to the correct page. All right, so always in our favor. Next, the gauge pressure. Now, the gauge pressure on the suction side of the pump we're talking about here, not the discharge side. That's the third part of the equation. And for an open system, it's really simple to deal with gauge pressure because gauge pressure is always 0. There's no gauge pressure present because if you think about an open loop system, the suction side of the pump is vented to atmosphere. So, for instance, if you were pumping out of a lake, well, there's no way to put a pressure gauge on a lake. It's just 0 feet of head. And gauge pressure with this particular type of gauge we're looking at is the value above atmospheric pressure. And we normally don't have any pressure above atmospheric on the suction side of the pump in an open system. So in an open system, gauge pressure is always 0. The fourth factor we have to concern ourselves with is vapor pressure. Okay, so what is vapor pressure about? It's a value that tells us something about how hard the liquid is trying to turn into a vapor. I forget my physics and so forth, but apparently liquids, would like to turn into vapors if they could, but there's forces that prevent them normally from doing that. But given the right circumstances, they would all want to become a vapor. But the force of the atmosphere is pushing down on that liquid. And that's what keeps it in a liquid state rather than in a vaporous state. So the atmosphere is pushing it down, keeping it liquid, but the liquid is pushing back up against the atmosphere. That's interesting. And if it can push up harder than the atmosphere is pushing down, then that liquid is going to become a vapor. Well, the amount of force that the liquid is pushing up with is called vapor pressure. And it gets more powerful as its temperature rises. That's why I've got a picture of a pot on my kitchen stove here. First time you put a pot of cold water on the stove, its vapor pressure is low. And it's not pushing up very hard on the atmosphere. And you don't see any vapor. Cold water. Turn the stove on. When the water temperature rises, the vapor pressure rises. And it starts to push harder and harder against the atmosphere. And when the temperature starts to get high enough, you start to see vapor. You can literally, as it gets hotter, you can see vapor coming off of it. Not quite boiling yet, but there is vapor coming off. And then finally, at 212 degrees Fahrenheit, at sea level, the water breaks into a boil. The fascinating thing about that is that's the point at which the vapor pressure pushing up has become equal to the atmospheric pressure pushing down. And consequently, that steam vapor forms and rises. So that's what's going on with vapor pressure. Well, how do we use that now? Well, this chart gives us the vapor pressure of water at various temperatures. And the higher the temperature, the higher the vapor pressure. And that's a bad thing for NPSH available. If you'll notice here at 70 degrees F, which I've got the red arrow on it, the vapor pressure in PSI-A is about a third of a pound. Okay, that's well under atmospheric pressure of 14.7 psi at sea level, so there's no vapor pressure. There's no vapor forming, I should say, excuse me. So that's the equivalent of about 0.8 feet ahead. It's not very much pressure pushing up on the atmosphere. But look here, at 212 degrees F, the vapor pressure is equal to, 14.7 psi, 14.696. That's why water starts to boil at about that temperature. That's the equivalent of about 35.3 feet of head. And that's a lot of pressure pushing up on the atmosphere. And again, that's why water boils at that temperature at sea level. Now remember, in our equation, we're going to have to use the feet rather than the PSI in the formula. So when using this chart, just keep in mind the vapor pressure is always going to be a negative value in the equation. And a large negative number is a bad thing for our pump. And that's why, let's say in steam boiler feed applications where you've got a condensate return pump tank and pump, you got very high temperatures, they are prone to cavitation. You got to take these calculations seriously. Okay, now we have suction line friction loss. And that's the fifth, and it's the last component of our equation. And what friction loss is, it's a deterrent to smooth flow into the eye of the impeller. You want that water coming in to be nice and laminar and smooth. But the friction, it's a restrictive force, and it's a negative value in our equation. You can calculate it by referring to tables and online calculators, and you have to make those calculations through not only the piping, but the valves and fittings and maybe strainers and other types of restrictions. You really want to take a good course in pump basics if you want to learn how to calculate friction loss. We can't do that today because of time constraints. But just remember, suction line friction is always a negative value in the equation. So it's a bad thing. We do not like friction loss in the suction line. So let's do a quick practice exercise. We've learned about the 5 parts of that equation, so here we're going to put it all together. The specification you can see is 750 gallons at 100 feet of head. It's an open loop system. You can see the tank. We have 8 feet of water above the inlet to the pump and the impeller eye. And for the sake of this exercise, let's assume that we're never going to be able to draw down that tank level. If we could draw down the tank or make it higher, it would make our calculations more difficult than we want for this simple exercise. So our altitude's 3,000 feet above sea level. Water temperature's 190 degrees Fahrenheit. I have pre-calculated 4 feet of friction loss through the suction piping system. So what is our NPSHA? Let's do an exercise. So first, let's start with the elevation head. Do you remember we had 8 feet of water above the pump? So that's an 8-foot positive value. We've plugged that in. Next, we need to do our atmospheric pressure calculation. We've got 3,000 feet of elevation. I'm going to bypass the PSI and go right to the feet of head, which is 30.4. That's a positive value. So we plug that into our equation up there at the top at 30.4. Next, we have to concern ourselves with gauge pressure. But remember, gauge pressure in an open loop system is always 0, so we plug that into our equation. Simple enough. We have our vapor pressure. And if you recall from the specification, we did have a water temperature of 190 degrees Fahrenheit. And again, I'm going to bypass the PSI reading and go right over to the feet of head. And it's 22.3 feet of head. So we can plug that in as the fourth value in our equation. Then our final one is our friction loss. And if you recall, I pre-calculated the friction loss for us. And if you want to learn to calculate that, go take a good course on it. I've pre-calculated our friction loss is 4 feet. And again, that's a negative value. So that's our fifth and final component of our equation. So we add and subtract, and what we get is a net positive suction head available of 12.1 feet. Not too terribly difficult. We just have to go through the process. Okay, so write that number down, 12.1. I've got 3 curves. We're going to see which one of these might be suitable for our application. They all meet the flow and head conditions of 750 gallons, U.S. gallons per minute at 100 feet. So again, down there in the lower right, the NPSH available is 12.1 feet. What's the NPSH required for curve A? Well, remember, we have to go to the curve itself and find that. There's our flow rate, and read off to the right, and we have a head NPSHR required of 18.5 feet. All right, if you need 18.5, but you only have 12.1 available, will the pump cavitate? And the answer is yes. It's just like if you've got $100 a month in income and $150 a month in expenses, your wallet is going to cavitate. Same thing here. 18.5 is more than the 12.1, obviously. So what about curve B? We don't want to use pump A. Let's take a look at curve B. All right. Will it cavitate? Well, the answer is maybe, because we have a net positive suction head required of 12 feet, and the net positive suction head required is 12.1. So, theoretically, you could lull yourself into thinking that would work. There are so many factors that could cause that not to work. What if you get scale buildup over time on the suction side of the pump and your friction loss on that side goes up slightly? What if your water temperature is really 194 instead of 190? So many things can go wrong. That's why you would want to apply that safety factor of 2 to 4 feet, and even then I would be nervous about this pump selection. So I would say no. We have a third curve. Okay, in the NPSH on this one, the requirement is 5.1 feet, and that's significantly less required than the 12.1 that's available, and therefore that pump would not cavitate. So, why would you want to use the other two when you have one that is, the requirement is well below the available? It's quite safe, and that would be a good selection. And again, even with that, keeping your adding your 2 to 4 feet of safety factor is just always a good precaution. So that goes through the entire process for an open loop system. Now let's shift gears a little bit, and we will look at a closed loop system. Okay, now as a rule, and this is just a general rule, don't take it to the bank, but as a general rule, cavitation is not an issue in a properly designed and installed closed loop, let's say hydronic hot water heating system. But we're going to take a look at the system so you'll understand why, and you'll also come to understand a couple of factors that can make this system not be designed or installed properly, and then you can have cavitation issues. And one of the keys to assuring you have adequate NPSHA for a closed system, it's the concept of something called pumping away. Let's figure out what that means. All right, so here's a real simplification of a hydronic heating system. You can see the boiler down in the lower left. The symbol towards the center top is the circulator itself, that little circle with the arrow in it. And one of the interesting aspects of a closed loop hydronic heating system, it's an area known as it's an area in the piping system that's called this point of zero pressure change. And it's the area that's located at the confluence of right there, where we have our expansion tank up and our makeup water supply comes in. And there's a pressure reducing valve that's used in conjunction with this. Now, in a typical residence, like the ranch house that I own, the pressure reducing valve is going to reduce the incoming city water pressure from maybe 60 psi down to, let's say, 12 psi. That would be typical for a residence. That number can be higher as you have more stories. But for our purposes, we'll just go with 12 psi. Because we have the city water pressure and we have a pressure reducing valve to go to 12, and we have that expansion tank that has a precharge on it, a precharged air pressure on it of 12 psi, it will hold the system pressure at 12 psi in the middle of that circle where these things all come together. And by the way, if the pressure regulating valve is set to 12 psi, then the precharge on that expansion tank has to be set at 12. It's the combination of those two things that causes the system pressure to always be maintained at 12 psi at that point. The reason that it will always hold pressure at that point is because you turn on the circulator, it adds its pressure head to the system, but the combination of the action of the pressure reducing valve and that expansion tank, that holds the system pressure at a precharged value. And that circulator can't change that 12 psi in this example, regardless of where we locate the circulator pump in the system. So it's going to be 12 psi at that point no matter what. Maybe that's a good thing. But the location of the circulator can have a really radical impact on the net positive suction head available in the system. So let's see how that works. Note the position of the circulator in this particular view. Now you see that pump icon now. It's the circle with the little arrow inside. That arrow indicates the direction of flow. So it's going to be clockwise around this loop through the boiler and back to the circulator via that point of zero pressure change, as you can see. And if you note, in this image, the circulator is pumping away from the point of zero pressure change. And that's critical, absolutely critical for proper NPSH and other system operating parameters. If the pump is located at any other point in the system, you can have some serious problems, including if the pump's position is in the wrong spot, cavitation is a real distinct possibility. Let's see how that works. So here's an exercise. Closed loop system, based on what we just learned. We've got 4 gallons a minute in our specification, U.S. gallons per minute, 23 feet of head, Denver area, 5,000 feet of elevation, 140 F degree water. The system pre-charge in the PRV, pressure regulating valve, are set at 12 psi, and there's a total of 1 foot of friction loss as we pump around the loop. So not much friction loss, pretty small system. So what would the NPSH be? Now, I want you to note that I've highlighted items 6 and 7 in red for a specific reason. This is a closed system. And unlike for the open system, for a closed system, we don't have to make the whole 5-part NPSHA calculation. And the reason for that is the point of zero pressure change is always going to hold its preset value, no matter what, regardless of the performance of the pump. That means that we only have to worry about what the precharge is on the tank in item 6 in the pressure valve setting. We just take that minus a bit of friction loss from item 7 between the point of zero pressure change and the suction inlet of the pump. That's all we have to determine, just two values, items 6 and 7. We can ignore all of the others. So, remember our system precharge is 12 psi. We convert that to feet of head by multiplying times 2.31 and get a value at that point of zero pressure change. There's a value of 28 feet. Now we got to take the one additional step now. And let's call this scenario 1. Note, the circulator is very close to the point of zero pressure change and is pumping away from it. And again, that's critical. We need to keep the friction loss through that little tiny part of the system as low as possible. And for our example, we're going to say we have a friction loss of only 1 foot in that area. Okay, then the head at the point of zero pressure change is 12 psi. We've converted that to 28 feet. From that, we have to subtract the friction loss value from the previous page, and remember I predetermined that for you at 1 foot. That gives us a total net positive suction head available of 27 feet. And by the way, we shouldn't have any problem at all finding a circulator that has an NPSH required value of well below that. That's scenario number 1 we just looked at. We were pumping away. Now let's take a look at scenario number 2. We've moved the circulator. Now notice it's still pumping clockwise around the loop, but it's no longer pumping away from the point of zero pressure change. Instead, it's pumping into it. So, we got a longer way around the loop. We're going to have higher friction loss on the suction side of the pump. Let's say there's 20 feet of suction line friction loss. That is significantly higher than when we were pumping away. And by the way, low mass boilers can have significantly high friction loss, so you've got to watch them. So with a friction loss of 20 feet, what's our total going to be? Well, remember, the friction loss is a negative value, so we had 28 feet positive at the point of zero pressure change, from which we have to subtract our friction loss of 20. That gives us only 8 feet of net positive suction head available. All right, so if you compare that to the 27 feet of NPSHA that we had when we were pumping away, you can see why the location of that circulator is absolutely critical to the proper functioning of your system, because you would have more challenges finding a circulator with only an NPSH R of 10 feet or more. I mean, you could certainly probably find one, but if you didn't choose the right circulator, you'd be in trouble immediately. You create all kinds of systems problems in addition to cavitation. Okay. Now, for certain types of pump, I mentioned way at the beginning of this webinar, the required inlet pressure, which correlates, right, the required inlet pressure correlates directly to net positive suction head available, and you can find it in data tables rather than on the curve. And this is particularly true for smaller pumps. The pressure required at the inlet of a pump is a function of the temperature of the water, as shown. If you look across the top of this chart, you can see increasing temperatures from left to right. So, for instance, this Model E requires only 2.1 psi, which is about 5 feet of head, if the temperature is 165 degrees Fahrenheit. But what happens if our temperature goes up? Well, if we have 190 degree water Fahrenheit, that requires 5.6 psi, and excuse me, that works out to about 13 feet of head. So you can see with temperature, once again, the values go up. So we're getting close to wrapping up now. There's some principles you need to keep in mind when you think about net positive suction head available. And the first one, very basic principle, the net positive suction head available from nature must be greater than the net positive suction head required by the pump itself. NPSHR and related data is either found on the curve itself or in a data book. And there's only 5 components to that NPSHA calculation for an open loop system, and then you only have to worry about 2 of them for a closed loop system. Here's a handy chart, a reference guide that we can provide to you. When you get these later, you can take advantage of that, and it asks you all the questions that you need to know before you start making the calculations. So it gives you a pretty good step-by-step guide. And I hope you agree that this isn't all that difficult. You just have to work your way through the processes one step at a time. So let's take a quick look at the objectives. Let's see if we hit them. We defined our terms. You've seen pictures of what can happen if you have bad NPSHA, and other system problems can occur as well. You can create a vacuum, so you suck air into systems where you don't want air. Other bad things can happen. We performed some calculations for both open and closed systems. We learned how to determine NPSHR from a curve and also from a chart, and then figure out whether or not for given applications you have a danger of cavitation occurring. So with that, I'm going to wrap it up and swing it back to Kevin for the Q&A period.
All right, Jim, thanks very much for the presentation. And again, thank you everybody for joining us for the webinar today. And we've already got a lot of good questions in here. So a couple of quick reminders. This webinar, we'll put it up as a recorded webinar on the Grundfos Technical Institute website. We hope to have that up in about 7 days along with the Q&A answers. So if we don't get to some of the questions, we're going to put those on our Q&A and attach those to the recorded webinar later. And so if you have any additional questions for Jim on the content, please go ahead and key that into the Ask a Question box, and we'll try to get to as many of those as we can during this Q&A section. All right, so we got a lot of questions early on, so I'm going to hit some of these that we got early. One of the, it was a comment / question. So it says, so to help improve NPSHA, should we avoid things such as multiple strainers on the suction side of the pump, air separator with strainer, Y strainer, suction diffusers, or things like that? Or would there be anything else we could add to help prevent NPSHA problems on the system side?
Well, the real simple answer, and it's too much of a simplification, the real simple answer is, avoid anything you can on the suction side. Strainers or elbows or whatever. But the fact is you can't. You can't ignore those, avoid those things and not use them. So the moral to the story is if you use them, make sure you accurately account for their friction loss when you do the calculations. And if you do that, and remember, if you've got variable flow systems, then you want to make those calculations at the highest flow, which is generally where your cavitation, where your NPSH required is the highest. As long as you account for all of those factors on the suction side, you should be okay. But, avoid elbows as much as possible. You want nice straight runs of pipe whenever practical. But, if you have to have a strainer because of trash in the system, you have to have a strainer. And you have to do maintenance on those strainers because as they start to clog up, the friction value goes up. And if you made your calculation based on a new strainer, when you first install it and there's no debris trapped in it, it's going to have low friction characteristics. But as it clogs up, it's going to get higher and higher, more and more friction. If you didn't account for that in your calculation, you'll cavitate, and it'll give you grief. So be cautious. There's no easy answer to some of these problems.
Yeah, you've told me of some of the horror stories. And then we got a question. So in the example that we had earlier, it showed an NPSHR is roughly 22 feet at 1,000 gallons per minute. Can you use a formula like the affinity laws to actually project the NPSHR at twice the flow, assuming we double the speed of the pump?
I would not use a formula like that. I would go to the curve and see what the flow is, or what the requirement is. Look at it from the curve. Yeah, I wouldn't trust it to calculations. In that case.
I was thinking the same thing. And then one of the questions is, so would you add the 2 to 4 feet of safety factor to the low NPSH pumps that have an NPSHR of 2 feet, so like steam condensate pumps?
Well, I'm going to say in an ideal world, yes, but I also know as a practical matter, those are critical questions on a condensate return tank, for instance. And what you very much need to do is have the conversation, with the boiler manufacturer if they provided the condensate return tank, which they probably did. Have the conversation with that tank provider and also with the pump OEM, and let them carefully evaluate it along with you. I think that would be prudent. Get as many knowledgeable people involved in it as possible. They can go in and look at their actual test data and see if there's a little room for you to eliminate using the safety factors, or if they say no, you better do it. So again, be cautious. I'm rather conservative by nature. That's how I would approach it, to try to stay out of trouble. Because once you get a big steam boiler system installed and you've got a cavitation problem, what are you going to do now? And who's going to pay for it? And what will the time delay be? And I don't think you want to go there. So, ask the questions and get as much help as you can.
Okay. And then one of the questions, and it had to do with the NPSHR and NPSH3. It says, so does adding 2 to 4 feet of head to the NPSHR equivalent to a NPSH3?
No. Those two things should be separated. And even if you're working with NPSH3, it would still be a prudent matter to put your safety factor in, of a few feet. NPSH3, the way that's derived, and I'm going to give you a simplification. You need to read the Hydraulic Institute standards if this is, central to what you do for a living. But when a pump manufacturer is testing a pump for NPSH required in the lab, they'll install the pump and they'll turn it on and they'll run it back at a low flow. They'll choke it back with a valve on the discharge side, and then they'll slowly start to open that, and they will take NPSHR readings on the suction side. I'm simplifying here. Well, as they open up that valve further and further, remember the NPSHR curve arcs up to the right. So they'll keep opening that valve, opening that valve, opening to that valve. When they get out towards the right-hand side of the curve generally, beyond the middle of the curve, there will start to be a slight drop in head. Just a slight drop in head. And at the point at which you get a 3% drop, is the point where the NPSH3 occurs. That's a simplification, but with only 5 minutes left to go, that's as far as I'm going to take it today. Read the HI standard. But again,
Okay.
I would still add 2 to 4 feet of safety factor.
Gotcha. And so one of the questions here, and it actually refers to HI, and so one of the questions was that for the NPSHA calculation we didn't add velocity to it in the calculation, and they've heard conflicting information on where HI stands on this. So does velocity need to be part of the calculation for NPSHA?
Well, there's a fascinating question for you, and I'm going to have to defer on that one. I could get myself and you in trouble probably pretty quickly on that one. I will do some research on it and make sure I have the exactly right answer, and we'll post that in our Q&A. My experience teaches me that when you're smaller pumps and lower flows, if you've got properly designed suction side piping, velocity head can become less of an issue, and that's different than the velocity in feet per second. But velocity head can become less of an issue. But when you get into large pumps, and particularly large pumps with low heads, and I'm thinking here maybe flood control pumps where you could have a couple 100,000 gallons a minute at 10 feet to get it over a levee. Those velocity factors on the suction side can become important for all sorts of reasons. So that's why I'm going to defer giving an answer today. Good question.
Okay.
Wish I had a clearer answer for you, but I don't.
I was going to say, I was looking for the answer myself. I was looking for the answer myself.
Okay.
So one of the questions said, so I see the calculation for NPSHA is absolute head. Is the NPSHR that we take from a pump curve also an absolute head? And is this a standard across the industry?
Okay. There is no standard NPSHR. Every impeller has its own unique characteristics based on its geometry, and probably the geometry of the volute also. Every impeller is different, so you have to go to the curve for that particular pump in order to determine what the requirement is. You can't do it by calculation or by generalization. You have to go to the manufacturer's curve. To do otherwise would subject yourself to real danger.
And would that NPSHR be considered the absolute head that you'd want for that factor?
I think I'd have to know what the intention of the questioner was in defining the word absolute. Just as a practical matter, I would say absolutely go to the pump manufacturer's curve. Yeah, and use that as the value that you're going to base your decision on.
Okay. If the person that stated that question, if you could define the question a little bit more and put that on the Q&A, we'll make sure we get that on our recorded webinar. That would help also. That would be great. Okay, and I think we got time for like maybe one more question. Okay, and so one of the questions was, for a negative value, does the value change as the volume of liquid in a suction self-priming scenario? So for a negative value, does this value change as the volume of liquid in the suction side, or like in a self-priming scenario? If so, how does this affect the equation?
I'm not sure I understand
I think that was when you were doing like a suction lift application. It showed you had one
Yeah.
with the tank above the pump and one with the tank below.
Yeah, yeah. And when you're into self primers, things get a little more complex. So let's defer that question and try one more,
Okay.
Kevin. I think we better set that one aside. It'd be too
Okay.
complex for this.
Yeah, and so and this is kind of a little similar but different, but is how does one account for the drop in pressure in positive elevation on the suction side of the pump?
How does one account for a drop in pressure if you've got positive suction head? How would there be? Oh, well, one way there could be a drop in pressure would be if, let's say you had an elevated tank that was 8 feet, when the tank was full, it was 8 feet above the center line of the pump. So you've got 8 feet of positive head, and that's, I don't know, 2 or 3 psi, whatever it works out to. But as you draw that tank down, let's say you've only got 2 feet of positive elevation head above the pump. Well, now you've got, only a psi. You've only got a couple feet of head. So in that case, what that would teach you is that you should always make your suction elevation head calculation based on the lowest water level in your suction source. If you're drawing down a tank, then you need to use the minimum level, not the maximum. If you're pumping out of a lake, you look at pictures of the lakes, Lake Powell out west. Behind those dams, the level of water can fluctuate tremendously. So you always need to base things on your lowest possible level. Kevin, do you think that answered the question?
I think so. Well, that's where I thought the question was coming from. So if it's different than that, once again, if the person that submitted that wouldn't mind clarifying just to make sure that we got that right, that would be helpful. All right. With that, we've reached the end of our time for our webinar today. So once again, we definitely want to thank everybody for joining us. Jim, thank you for the presentation and your knowledge today, and we hope everybody has a good day. And thanks for joining us. Goodbye.